In this video, I'm going to talk about Latin squares. So Latin square is a table n by n, n by n. The cells of this table are filled with the numbers from 1 to n. So each cell is filled with the number, and basically the condition is that each row must contain exactly one number, exactly one occurrence of each number. So like it must contain the number 1 must occur once, the number 2 must occur once, the number 3 must occur once, and so on. So each number 1 must occur exactly once in each row, and the same holds for a column. So each column also must contain exactly one occurrence of each of these n numbers. So let's write this as a definition. A Latin square is a table n by n filled with numbers from 1 to n, such that each row, or let's put it this way, such that each number from 1 to n occurs in each row and in each column. Exactly once. Yeah, or another way to put it is like if each row and each column contains exactly one occurrence of each number. Yeah, so that's the definition. So first let's consider an example, right? So if we have a table, let's say let's say first 2 by 2, right? So the simple example is like if you put 1 here, like there is no other way than to put 2 here, then here must be 1 because 2 is already in this column, so it must be 1. Here it remains only 2. So this is a Latin square of order 2. Yeah, and by the way, n is called an order of the Latin square. So n is the order. So here I should add Latin square of order n is a table and so on. Okay, so this is the Latin square of order 2. So now if we consider like order 3, so without loss of generality we can put 1 here. Well, let's fill, well, yeah, so like I think it would be easier to construct for arbitrary n. So yeah, so basically we write that theorem that Latin squares exist for any order. So for any order, there exists Latin square of order n. Yeah, so let's consider now the proof of this theorem. So the proof would be by a direct construction. So we have our table n by n, and what we do basically is we put 1 on the main diagonal. So we fill the main diagonal with 1s. So 1 and so on, and the last would be here. Okay, so then we put 2 on the diagonal, like one step to the right and to the like upwards from the main diagonal. So here we put 2 and so on. 2 would be here, but since there is the number of these items on this diagonal is n minus 1. So here we have n minus 1 of 2's, right? Of 2's. So in order to have n 2's, we basically consider this diagonal to be shifted to the first. So basically we consider this square, this cell, to be belonging to the same diagonal. So, and we put 2 here as well, because you see, like this square, it doesn't lie in the same row with any of the items on this diagonal, right? If you consider this diagonal with 2's, and this, we consider this to be a part of this diagonal, because like like we can also write it modulo n. So like the next 2 should be here basically, right? Here, but it is so the row index would be n plus 1, the column index, and the row index would be n. So we keep the row index, but the column index we shifted by n. We subtract n, which is basically means that we consider it modulo n. Modulo n, like this, would be like 1, right? So we move this 2 here. So yeah, like this is not exactly best way to write it, but I think you understand my point. Yeah, so the next one we put 3 here, 3 here, 3 here, and so on. The last one would be here, and in a similar manner we continue, so 3 should be here and here, two remaining 3's, and we shift it to the board modulo n, so they would be here and here. And so, and we continue the same way, then would be 4, and so on. And the last one would be n. N would be here in the last cell, and for this diagonal basically would correspond to the next diagonal here. So n would be here, 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 so on, here. Yeah, so basically we filled this by diagonals. So in each diagonal, modulo n, there is the same number. So we observe now that by construction, so any row it intersects exactly one diagonal. So therefore any row contains, so let's write this. So any row intersects exactly, well, any row intersects each diagonal exactly once. Each diagonal exactly once. Therefore, like every it's better to write not any row but every row or each row. Each row, therefore, each row contains each number exactly once, because like the numbers are filled by diagonals. And the same for columns. Well, like we also noticed that the like it doesn't matter. So yeah, so similarly for columns. So like every column intersects each diagonal exactly once, and therefore each column contains each number exactly once. And so from this statement and from this statement we conclude that it is a Latin square. By definition. And this so basically concludes the proof, because we directly constructed the Latin square of an arbitrary order n. Yeah, so they exist for every n. So that's it for this video.